In this video, I explain the proof of Cauchy's second theorem on limits. What is the first theorem? First theorem is if limit xn is L, then limit x1 plus x2 plus xn upon n is also L. Am I correct? This is Cauchy's first theorem on limit. What is that? If limit xn is L, that means xn converges to L, then the sequence x1 plus x2 plus xn upon n also converges to L. Then the sequence given by this also converges to L. What is the second theorem? Second theorem is like this. If limit xn, yes, if limit xn is equal to L, if a sequence xn converges to L, then limit xn plus 1 upon xn is also L. What is the theorem? If xn converges and limit xn plus 1 upon xn is L, then repeat. Second theorem is like this. If sequence xn converges, then and limit xn plus 1 upon xn is L, then limit xn raised to 1 upon n is also L. Xn raised to 1 upon n is L. This is second theorem. See, the theorem is like this. If xn converges, it is a sequence of positive terms, and limit xn plus 1 upon xn is L, L may be finite or infinite, then limit xn raised to 1 upon n is L. Limit xn raised to 1 upon n is L, or limit xn raised to 1 upon n is limit xn plus 1 upon xn if xn converges. Xn converges. This is second theorem. See, these theorems, two theorems are helpful while evaluating the limit of sequence of positive terms. Now, proof of the theorem. I think all of you followed what is the statement. If xn is a sequence of positive terms and limit xn plus 1 upon xn is L, where L is finite or infinite, then limit xn raised to 1 upon n is also L. So limit xn raised to 1 upon n is limit xn plus 1 upon xn. I explain how we can apply this theorem to solve the problems. Now, to prove this, we take first case is L is finite. Limit xn plus 1 upon xn is L, and L is finite, first case. What do you have to prove? We have taken limit xn plus 1 upon xn is L, and we prove that limit xn upon limit xn raised to 1 upon n is L. For that, we start with this. Therefore, if limit is L means, you know the definition of limit of a sequence. Therefore, for epsilon greater than 0, there exists m belongs to n, however large, such that mod xn plus 1 upon xn minus L is less than epsilon. Is less than epsilon by 2 for all n greater than or equal to m. How to write this step? This is by definition of limit of a sequence. If limit xn plus 1 upon xn is L, then what is the meaning of limit is L? For epsilon greater than 0, there exists m belongs to n such that xn plus 1 upon xn minus n is less than epsilon by 2 for all n greater than or equal to m. This implies by using inequality of this absolute values, L minus epsilon by 2 less than or equal to xn plus 1 by xn less than or equal to epsilon by L plus epsilon by 2 for all n greater than or equal to m. Using this definition of absolute values, we know that mod x minus a less than delta implies a minus delta less than x less than a plus delta or equal to less than or equal to a plus delta. We have used this definition of or inequality of that absolute value. Now this is for all n greater than or equal to m. Therefore we substitute n is equal to m, m plus 1, m plus 2 and so on, n minus 1. What is this? So we have started with this limit xn plus 1 upon xn is L, and what we have to prove? If this is xn plus 1 upon xn is L, then the limit xn raised to 1 upon n is also L, and by definition of limit xn plus 1 upon xn is L means we have this: for epsilon greater than 0 there exists m, so that for all n greater than or equal to m we have this. Now since it is true for n greater than or equal to m, we can put n is equal to m, m plus 1, m plus 2, so on. Here in this expression what you get? L minus epsilon by 2 less than or equal to xm plus 1 upon xm less than or equal to L plus epsilon by 2. L minus epsilon by 2 less than or equal to xm plus 2 upon xm plus 1 less than or equal to L plus epsilon by 2, and so on. L minus epsilon by 2 less than or equal to xn upon xn minus 1 less than or equal to L plus epsilon by 2. Now here we have these inequalities here. How many inequalities are there? N inequalities are there, because m to n minus 1. We can take this as m to n minus 1 means n minus how many inequalities are there? If it is 0 to n minus 1, then it will be n. But we have not started with 0, it started with m. So n minus m inequalities are there. Totally n minus m inequalities are there. Multiplying these n minus m inequalities, we get L minus epsilon by 2 raised to n minus m less than or equal to, see this side, how many L minus epsilon by 2 are there? N minus m. So multiplying we get L minus epsilon raised to n minus m less than or equal to, but here these terms get in pairs. Xm plus 1 cancels, xm cancels, no, xm doesn't cancels, xm plus 1 cancels, xm plus 2 cancels, finally xn minus 1 cancels. So we have xn upon xm less than or equal to L plus epsilon by 2 raised to n minus m. So multiplying we get this. What we are going to prove now? Limit xn raised to 1 upon n is also L. Xn upon xn for this step. Therefore L minus epsilon by 2 raised to n minus m into xn less than or equal to xn less than or equal to L plus epsilon by 2 raised to n minus m into xn or L minus epsilon by 2 raised to 1 upon n minus m by n into xn raised to 1 upon n less than or equal to xn raised to 1 upon n less than or equal to L plus epsilon by 2 raised to n minus m by n into xm raised to 1 upon n, taking nth root on both sides or raised to the power 1 by n. So we get xm raised to 1 upon n into L minus epsilon by 2 raised to 1 minus 1 upon m, correct? 1 minus m by n is less than or equal to xm raised to 1 upon n less than or equal to xm raised to 1 upon n into L plus epsilon by 2 raised to 1 minus m by n. Here n minus m by n can be written as 1 minus m by n. So we prove that xn raised to 1 upon n is also L. Now take this as 1, this as 1. We simplify further like this. We take n tends to infinity now. As n tends to infinity, xn raised to 1 upon tends to 1 and L minus epsilon by 2 raised to 1 minus m by n tends to L minus epsilon by 2. How to get this? So xm raised to 1 upon n means as n tends to infinity, this is terms are positive here. Positive. So xm raised to 1 upon n tends to 1 and L minus epsilon raised to 1 minus m by n, because m by n tends to 0 as n tends to infinity, becomes L minus epsilon by 2. Therefore this implies, what does this implies? L minus epsilon by 2 raised to n minus m by n tends to L plus epsilon by 2. This implies for epsilon greater than 0 there exists positive integers m1 and m2 such that, so what is the meaning of xm raised to 1 upon n becomes 1 as n tends to infinity, implies xm raised to 1 upon n into L minus epsilon by 2 raised to 1 minus m by n minus so xm raised to 1 upon n tends to 1 and L minus epsilon by 2 raised to 1 minus m by n tends to L minus epsilon by 2. Therefore mod xm raised to 1 by n into L minus epsilon raised to 1 minus m by n minus L minus epsilon by 2 is less than epsilon by 2 for all n greater than or equal to m1, because this xm raised to 1 upon n L minus epsilon raised to 1 minus m by n tends to L minus epsilon by 2. Therefore the mod is less than epsilon by 2. And xm raised to 1 upon n L plus epsilon by 2 raised to 1 minus m by n minus L plus epsilon by 2 is less than epsilon by 2 for all n greater than or equal to 1, because as n tends to infinity, this xm raised to 1 upon n becomes 1, L plus epsilon by 2 raised to 1 minus m by n becomes L plus epsilon by 2. So this as n tends to infinity becomes L plus epsilon by 2. Therefore this minus L plus epsilon by 2 less than epsilon by 2 for all n greater than or equal to m2. Now simplify this using again inequalities. This implies xm raised to 1 upon n L minus epsilon by 2 raised to 1 minus m by n is greater than, correct, is greater than. Now we apply this mod x minus a less than delta implies a minus delta less than x less than a plus delta. Apply this. So it is mod x minus a less than delta form. So this xm raised to 1 upon n, compare with this compare this with a mod x minus a less than delta, we get xm raised to 1 upon n L minus epsilon by 2 raised to 1 minus m is greater than L minus epsilon by 2 minus epsilon by 2 and less than L minus epsilon by 2 plus epsilon by 2. This is for all n greater than or equal to m1. Correct? M1. And second one, for all n greater than or equal to m1. Therefore, L minus epsilon less than xm raised to 1 upon n into L minus epsilon by 2 raised to 1 minus m by n, which is less than L. Less than n. And second one, xm similarly, xm raised to 1 upon n into L plus epsilon by 2 raised to 1 minus m by n is greater than L less than L plus epsilon. Less than L plus epsilon. L plus epsilon. For all n greater than or equal to m1, for all n greater than or equal to m2. Say, using xn plus 1 upon xn is L as n tends to infinity, by using that definition we have obtained this step, these two. Now, take this as 2, this as 3, and you go back to the step. I explain what is that. We have taken, or we had come across xm raised to 1 upon n into L minus epsilon by 2 raised to m by n is less than xm raised to 1 upon n less than xm raised to 1 by n into L plus epsilon by 2 raised to n minus m by n. Say, we came across this step. I give number for this as 1. This is 2, this is 3. Now, using 1, 2, 3 and taking P is suppose maximum of m1, m2 and m, because this is for all n greater than or equal to m. This already you have taken, this as 1, 2, 3. Now P is maximum of m1, m2, m3. Then we get L minus epsilon less than, see from this, what is xn raised to 1 upon n, L minus epsilon raised to m by n less than xn raised to 1 upon n. But this is greater than L minus epsilon. So, xn raised to 1 upon n, which is less than L plus epsilon. Less than L plus epsilon. Because, see this, xn raised to 1 upon n is less than xn raised to 1 upon n, L plus epsilon raised to n minus m by n. Now, using 3, this xn raised to 1 upon n is less than L plus epsilon. Using 2, xn raised to 1 upon n is greater than L minus epsilon for all n greater than or equal to P. This implies xn raised to 1 upon n minus L is less than epsilon for all n greater than or equal to P. Therefore, limit xn raised to 1 upon n is equal to L. So, when L is finite, we have obtained limit xn raised to 1 upon n is also L as n tends to infinity. Now, suppose L is infinite. L is infinite. We can extend this proof, case 1, L is finite, to infinite L when L is infinite also. Let limit xn plus 1 upon xn as n tends to infinity is L. Therefore, what is L? Infinite. L is infinite means limit xn upon xn plus 1 n tends to infinity is 0, because reciprocal of this 0. Therefore, limit 1 upon xn plus 1 divided by 1 upon xn n tends to infinity is 0. Write this as 1 upon xn plus 1 divided by 1 by xn. Xn by xn plus 1 is written as 1 upon xn plus 1 divided by 1 upon xn. Now, by case 1, from case 1, limit 1 upon xn raised to 1 by n is 0. What is case 1? Xn plus 1 upon xn is L. Xn plus 1 upon xn is L. Then xn raised to 1 upon n is L. Now 1 upon xn plus 1 upon xn is L. So 1 upon xn raised to 1 by n is 0. This implies xn raised to 1 by n is infinity. This is L. This is L. So we can extend that case 1 to the case when L is infinite also. And go through the proof. This proof from examination point of view it is important. Proof is asked in previous examinations. One simple application is prove that limit nth root of n is 1. Very fine application of this Cauchy's second theorem is this: limit nth root of n is 1. By second theorem we have limit n raised to 1 upon n is limit n plus 1 by n if exists finitely. It is therefore limit it is equal to limit 1 plus 1 upon n tends to infinity, therefore 1. Now it is n raised to 1 upon n form. What is limit n raised to 1 upon n? It is limit n plus 1 by n. What is Cauchy's theorem? Limit n raised to 1 upon n is limit n plus 1 by n. But what is limit n plus 1 by n? 1. So limit n raised to 1 upon n is also 1. That is the application of Cauchy's second theorem. Yes, I solve some more examples on this in the next video. Okay, thank you.